All right, in the previous video, we established or highlighted the difference between types of continuity, two types of continuity. We had, in the first case, a linear function, and when we went to establish that it was continuous at every point C, we can do that with a single choice of delta, right? The delta sub epsilon in our proof of continuity turned out not to depend on the point C that we chose at the outset. Now we contrasted that with the function g of x equals x cubed, where it turned out that a single delta wouldn't do it. In other words, the delta sub epsilon that we ended up with depended on the value of c. It depended on the point we were interested in. So that kind of splits those functions along an important line. The first function we will now say is a uniformly continuous function on R, where the second example, x cubed, was not uniformly continuous on R. And again, the difference is, on the one hand, we had a delta that worked for all points at the same time, and on the other hand, we had a delta that depended on the point we were interested in. Well, here's the formal definition for that idea. F with domain A mapping to R is uniformly continuous on A. If for every epsilon bigger than 0, there's some delta bigger than 0, such that whenever x and y are within delta of each other, f of x and f of y are within epsilon of each other. So in other words, we can make f of x as close as we like to f of y just by taking x and y close enough together. And notice this delta doesn't depend on the y, right? It doesn't depend on the x. It only depends on how close they are together. And this has to work for every pair xy in the set A. Now we're going to use the definition to establish uniform continuity for one of our examples in just a moment. But this theorem is often the easiest way to establish uniform continuity, because all it requires is that you start with a function you know is continuous, in kind of our usual sense. Then if you have a continuous function and the set you're interested in is compact, in other words, closed and bounded, well, then you automatically get f is uniformly continuous on that compact set. Right, so it's not true in general that continuous functions are uniformly continuous, but it is true that continuous functions on compact sets are uniformly continuous on those sets. So that's why the example we're about to do doesn't contradict what we did in the previous video. There we gave an indication that x cubed is not uniformly continuous on R, but that's okay because R is not a compact set, right? G is continuous, R is not compact, so the theorem doesn't apply. If we restrict our attention to, say, the interval 0 to 2, that is a compact set, and so the theorem now automatically guarantees that, in fact, x cubed is uniformly continuous there. But we should get a little bit of practice working with the definition, so we're going to use the definition kind of to go the long way around and establish this directly. So let's let epsilon be bigger than 0, and we consider the thing we want to make small. So that's, g of x minus g of y, which is x cubed minus y cubed, which by difference of two cubes is this. Right, so we pull the x minus y out of the difference of two cubes, and we're left with x squared plus xy plus y squared. Now, as in previous problems, I want to get a bound for this. Maybe I'll use the triangle inequality first. And now we use the fact that both x and y live in this interval 0 to 2, so the largest that absolute x or absolute y can be is 2. So this then has to be less than x minus y times 2 squared plus 2 times 2 plus 2 squared. So that's the same as x minus y times 12. Now we want to make that less than epsilon, and this reveals the choice for delta. Right? If we divide both sides by 12, so this happens, and x minus y is less than epsilon over 12, so there's my delta. And notice that it doesn't depend on the particular points that we've selected. It only depends on the epsilon. All right, so then if x minus y is less than delta sub epsilon, we have x cubed minus y cubed. That's less than x minus y times 12, which is less than epsilon over 12 times 12 equals epsilon, and this happened for all x and y in the interval at the same time, and so that establishes the uniform continuity of x cubed, provided, right, we are focusing on a compact set as we are in this example.